Okay, guys, what we're going to do. All right. In terms of the amino acids specifically and the level of detail, okay, it is relatively easy. Let's talk about how many amino acids do we need to know catabolically. We need to know 20 of them, okay? We know how they're broken down. For most of them, you just need to know what amino acids starting with and what do you get as a product, okay? And where it goes into the Krebs cycle or whatever, okay? So for instance, if you know it's a 4-carbon amino acid, like aspartic acid, you know that it's going to end up as OAA, which will eventually go to glucose, all right? There are breakdown pathways which are more complex that have more errors of deficiency diseases in the pathway, okay? So if they're that way, so for instance, the breakdown of methionine, okay, is to homocysteine by that methylation process, okay? And then we get homocysteine. But homocysteine can then be combined and make cystathionine, and then you get cystathionuria, so that's an inborn error. And then it gets broken down to cysteine, and you can get cystathionuria, okay? And so that pathway of methionine, so in the breakdown pathway, I highlight that pathway with the level of detail. So for breakdown and deficiency diseases, you always want to focus on where there's a deficiency, okay? But for the majority of them, of the 20, probably 12 out of 20, you just have to know, start with this amino acid and go to this, okay? Is that clear to everybody? Okay. In terms of the synthetics, the amino acid anabolism, okay? And so we're going to do that on the second lecture on Monday, okay? Is the catabolism. The anabolism is a different thing. I don't need to know how the essential amino acids are made. We let the bugs and the animals and whatever doing it, okay? And you just give me the amino acid, okay? And it's you know, and so you only need to know for the non-essentials. And for many of the non-essential amino acids, the process is just the reverse of that. So for instance, remember I said we could go from glycine to what? That's reversible. So we can go from serine to glycine, and we can go to, it's reversible. We can go from glycine the other way, or we can go from the cleavage enzyme, okay? So, all right, so, which is then the glycine cleavage enzyme breaks it down, okay? But then it can go in the other direction, and it's called glycine, glycine synthase, okay? So is that clear to everybody? So the anabolism is really not that terribly important, okay? The inborn errors, so if you want to search for the inborn errors in pathways, that's really what. Does that clarify it for everybody? Okay. So I'm nasty, but I'm not that nasty, okay? So, and I don't write the tests, okay? So, we're going to focus on that. Your goal as physicians in training is to look for where there are going to be deficiency diseases in the pathways, okay? And I think we've highlighted them enough, okay? There aren't a lot, okay? Is that clear to everybody? Okay. So important to know what essential and non-essential, okay? And kind of whether they're gluconeogenic or not, okay? And then visualizing it on that basis, okay? If you still can't remember the dog ate your notes for the TCA cycle, you really ought to review it, okay? Because that's important to know, at least in terms of the numbers, you know? I take a 2 and a 4 and I make a 6, and then I make a 6 and another 6, and then I make a 5, and then I make a 4, and then I make another 4 and different oxidation 4s, okay? So, and learning the number of of carbons in the amino acids will help you, okay? All the 3s go to pyruvate, okay? The 3 carbon amino acids go to the pyruvate, okay? They are serine, pyruvate, they're pyruvates, serine, alanine, and what? Cysteine, yeah. You have to be careful with cysteine because you have cysteine, which is the dimer, okay? And so you have to be very careful when you say, you should emphasize the EI, cysteine, yeah, okay? It will help you to do it. It's the same with hypo and hyper. You have to be really careful to say hypo, hyper. Okay, so it's useful. Okay, all right. So what we're going to do now is we're going to actually look at the names of bases. Okay, and this is hopefully basic for you. The only problem is that there's a couple of kinks in the process. Okay, all right. Okay, so let's first of all decide what the difference is between a nucleoside and a nucleotide. So a nucleoside is what? A base and a sugar. The sugar can be ribose or deoxyribose. Okay, you can then put a D in front of it. Okay, right? Okay. What about a nucleotide? It's a phosphate, 1, 2, or 3 phosphates. Okay, are nucleotides. Enzymes that work on them will have names that will be like nucleotidase, okay, which means that it works on a nucleotide, not on a nucleoside, okay? And so it's important that you distinguish it, okay? All right, so that's one of the things. The other thing is that, so here's the names of the bases, adenine, guanine, okay? So adenine, the nucleoside is adenosine, and what would be the nucleotide? AMP, ADP, ATP, adenosine monophosphate, diphosphate, triphosphate, okay? So that would be the same. Guanine is easy. Guanine is guanosine, okay? So it looks like you got a pattern going. Osine must be nucleosides, right? Until you get to cytosine, okay? Which is the base, which then goes to cytidine, which is the nucleoside, okay? So you have to be careful with it that way. It gets worse. Okay, thymine is a pretty thing, but the important one is the sugar in thymidine is which? Deoxy, right? Because it's in, right? It's the one that's going to be used in, right? So you don't have to say D-thymidine. I think in the dump to D-thump there's a D in that. You don't need to do that. Okay. Okay. Then we have uracil, and uracil is just this all no home part. It's not uracillose or some ene, okay? It becomes uridine. But the one that's a killer, okay, is hypoxanthine, okay? The base is hypoxanthine. We're going to see it at the end of this lecture and in the middle, and I'll show you the structure, okay? All right? Hypoxanthine, and its nucleoside is inosine. Now, you've already seen it, and where did you see it? Yeah. The wobble effect, very good, right? They call it I in it, okay, so it's inosine, but what's the base? Hypoxanthine. Yeah, right? Okay, so you're right, but yeah, okay. We have to have a culture dollar, and I don't know, this is a 2-part culture dollar, hopefully, that you can do it, okay? Who developed the first polio vaccine? Yes. Jonas Salk. Very good. Excellent. So you get $1 for that, okay? Why is that important to this building? Yeah. He graduated from City College. Okay, so that's the so you get 1. Okay, and we'll pass this back to our friend in the middle back there, not that $5. Take it from the little one. Yeah, okay. All right. But my question for you is, most of you did not have Salk vaccine, okay? What polio vaccine did you have? And who developed it? What? You don't have any idea, right? My guess is that you had the Sabin vaccine, okay? And does anybody know the difference between, other than the names, the difference between the two? Yeah.
One of them was live. I know them.
Yeah. So which one? Yeah. What?
Sabin was live?
Yeah, it was live, yeah. Whereas Salk, they didn't know enough about it. Polio in the 40s and 50s was terminated summer vacations for everybody because they always thought it was associated with water and pools and everything. And it was, and the kids were treated in iron lungs. It was just a horrible disease. So you had no summers in the early 50s until that. So it was a real thing. So they would use the dead vaccine, okay, first, and then Sabin was that. So that's a good answer. So that was the other half, which I should have another single. That's a 5. Okay. What? No, she deserves it. No, it was a good answer. You should always know who develops what you do. I used to be on the Salk committee at that time when I used to be on the Salk committee when people who were going to come to Sophie Davis could get scholarships, and we had to select, and it was the participating medical schools, and at that time Mount Sinai took students from Sophie Davis in the early program, so it was the Jonas Salk one. So I don't know. There's probably a scholarship still in his name.
I don't know. I know at Hunter there is.
Really? Yeah. Did he go to Hunter too?
I don't know.
I don't think so.
I know they
Yeah.
have a Salk award.
Yeah, his brick is out there somewhere. Right? Out in the yard there.
We'll go out and
Find Jonas Salk. Yeah, dedicated brick. Okay. All right. So just to try to keep it safe with it, okay, so we have to distinguish between nucleosides and nucleotides. Okay. All right. So here there's structure. The other thing is, this is thymine, okay? You have to be careful with not confusing it with thiamine, which is a vitamin, okay? So thiamine pyrophosphate. So you have to say each of the vowels so that you can actually distinguish it on that basis. So, okay, all right. Those are the pyrimidines and so. All right. So there's the oxyribose, in which there's an H there, and it's a hydroxyl group when it's ribose. Okay. All right. So here we have nucleosides, nucleotide, monophosphate, triphosphates. These are all nucleotides. Okay. And this is you knew already. Okay. So this is the structure of a choice is purine or pyrimidine. Purine. Big ring, 2 rings. Okay, short name, purine. 1 ring, long name, pyrimidines. Okay, categories. Okay, so that's the way to remember it. I still to this day did it. Okay. When I was in graduate school, that was when the Watson-Crick model came out. Okay, so that's a long time ago. So they were dealing with it. Okay, so this is a purine. There are 2 rings. You really don't need to know the numbering on it, but what you need to have it do is that it's going to be built up from other molecules, parts of other molecules. Okay, and so you need to know what contributes to get the structure. Okay, all right. And there's a set order in terms of what we want to take a look at. So let's look at the structure. Okay. Interestingly enough, the purines are made on the sugar. So you're going to actually do it. So it's kind of like a way of kind of building blocks. So there is a building block where you're going to start with ribose 5-phosphate, or a part of a molecule, which we'll talk about in a minute, okay? And you're going to build the molecule on that and then build it that way, okay? So let me go and take a look a little bit. Okay. I think we can go back. All right. Okay. So the things that are going to make, so the big ring has 2 nitrogens in it, 1 and 3, okay? The small ring has 2 nitrogens in it, okay? 7 and 9, okay? Now, the first thing that we're going to do, okay, and we'll go over this later on too as well, is that the amide nitrogen of glutamine, okay, is going to go in first, and it's going to go on to ribose 5-phosphate. We'll see how you do that, but okay, that's the first thing. So I've got ribose 5-phosphate with a nitrogen on it. That nitrogen, the amino group, which is now coming from the amide amino. Remember, there's an amino one there as well, okay? Whenever glutamine donates to large molecules, it always donates the amide nitrogen and goes to glutamate, okay, on that basis, all right? So then the next thing is that this amino acid, which is a 2-carbon amino acid, which you should know as the only 2-carbon amino acid is glycine, okay? And it goes in, here's the nitrogen and here's the 2 carbons, okay? And so that goes in, and there's a linkage here at this point, all right? And then the next one will be this one, N10-formyl tetrahydrofolate. So what's the N10-formyl? The carbon is at what oxidation state? Carbonyl, right? Yes? No? N10-formyl. So what it's going to do, and you can't see it here, this comes in, and there's going to be a double bond ending up with an N, okay? All right? With this N on this point, okay? So that's where it's coming in. So first this, then this, then this, and then, interestingly enough, this nitrogen. It also comes from glutamine. When glutamine donates, it always goes to glutamate, and it's the amide nitrogen which goes in. And then I close the small ring, okay? Then what happens is CO2 comes in. Now, when CO2 comes in and added to a molecule, what do you think the cofactor is? Biotin, but it ain't. This is a carboxylase which doesn't use biotin, okay? So it gets it that way. Now what's going to happen here is that this nitrogen is going to come from aspartate. We saw in the urea cycle when aspartate donates its nitrogen, okay, which is its amino nitrogen, what do you get? What? You usually get fumarate, okay? Okay, you get fumarate, okay, all right, so that's what it is. And so when aspartate, which aspartate and aspartic acid and glutamine are the major nitrogen donors to big molecules, okay? Which this isn't terribly large, but it will become a larger molecule eventually, or part of a larger molecule. And then this carbon, N10-formyl, okay, this carbon comes in here and we're going to end up with a double bond in that position, okay? So this goes in first, this goes in second, then this is third, then this is fourth, and then this is fifth, then this is sixth, and this is seventh, and then you close the big ring, okay? Relatively simple. All purines have the same sources of what's going on. Yes? Yeah, okay. I think it'll make more sense when we go to the next slide, okay? Okay, but you want to think of it that way, okay? All right, this is the order of synthesis, okay? So the initial process, we're going to use ribose 5-phosphate. Where does the ribose 5-phosphate come from? What pathway? Pentose phosphosine. Good, you haven't forgotten the stuff that you learned, okay? Remember, that was one of the functions of the pentose phosphate shunt, was to make ribose and 5-carbon sugars, all right? Okay? By the way, we haven't made deoxyribose at this point, okay? All right, so what's going to happen? This is now ribose 5-phosphate with ATP, and we're going to get phosphoribose pyrophosphate, okay? Which is a high-energy compound, okay? And it's going to have a way of effectively being cleaved, and what's going to happen is that I'm going to this is the first process, okay? So the first step, which we'll see here, I think. Yeah. Ribose 5-phosphate with PRPP synthetase. Okay, why is it a synthetase and not a synthase? Because there's ATP there, okay, and you go to AMP and you get 5-phosphoribosyl 1-pyrophosphate. It's abbreviated PRPP, okay? All right, so that's the building block. It's not the only thing, the next step, which is glutamine coming in, is not the only thing that uses PRPP. Now, the making of this molecule, we're talking about de novo synthesis of it, okay, from a lot of small pieces. You saw them, an amino group here, a carbon group there, another carbon group here, a CO2 group there. The only big piece is glycine, which is 4 atoms, okay, or 5 atoms, okay. So that's what's going on. So let's go back, all right? So PRPP combines with that, and we're going to get the amino group is going to So that goes in first, and then the glycine goes in, and then the N10 formal goes in, right? So I have it down in numbers. If that, I think that'll help rather than me wandering around. So the first one is from went the wrong way. Okay. So the first one is glutamine and PRPP. So this is, I will put a 1 here. Okay. Okay. One here, 2 here, glycine comes in, 3 here, formal group comes in, then 4 here, okay, and 5, because you're doing 2 things. You're putting in glutamine and you're taking in, you're using ATP to close the ring. Then the CO2 is 6. The aspartate is, the CO2 is 6. Then the aspartate is 7. Or after the aspartate is 7, then 8. And then 9 is closing the big ring. So does that help a little bit? So I know. Does anybody want to say what I said? Okay, so here. So this is 1, 2, 3, 4, 5, 6, 7. I cooked it. So let me read it to you. So it's 1, 2, 3, 1, 2, 3, 4 and 5, 6, 6, 7, 8, and then 9 is closing the big ring. Okay? All right. All right. Yes?
Do we need to know the exact order, or we
Just know that they're stepped, yeah. Nobody's going to say yeah. Just to know where they are. So all the little pieces are put together. You need to know the pieces are. So it's 2 glutamines, okay, 2 carbonyl tetrahydrofolates, okay. In olden days, they were differences, okay. And so what we're going to do is make IMP. So what's the base? What? What? Hypoxanthine. Hypoxanthine. Okay. Okay. So, one of the ways to remember it, xanthine, which we'll see, okay, hypo means less than. So less than xanthine, and we'll see. Yeah, I'll show you. This is the structure xanthine. Hypoxanthine has 1 carbonyl. Hypoxanthine has 1 carbonyl. Xanthine has 2 carbonyls. And the ultimate product, which is uric acid, has 3 carbonyls. Okay? And that's how it's metabolized. So here's hypoxanthine, 1 carbonyl. Here's xanthine, which is 2 carbonyl. And they both purines get metabolized to uric acid. 3. Uric acid is one of the nitrogenous products that we excrete, okay, from purines. Purines are made into the large molecule, and they're actually let go by as a large structure. The ring structure stays the same. Okay? Or is that making sense? Okay. All right. So let me go back. Okay. Okay. So we make hypoxanthine, so that's really what's going to happen. Okay, so what we really need to know for making DNA or RNA, right? We need to know that we have to make a G form and an A form, right? Okay? All right. And C and T, no, we don't have to worry about that yet. Those are the pyrimidines, okay? All right, so we're doing good. Okay, so IMP, and we're going to go through this specifically, okay? IMP gets converted to ATP, to AMP, and then to ADP, and then to ATP, and it also can get oxidized. There's an oxidation for this because this is actually becomes XMP, and I get GMP and dealing with it for RNA. Okay, so that's a schematic. I wouldn't worry too much about it. Oops. I just killed this. Okay. Sorry. Okay. So let me catch up with my notes because I move things around. Okay. So ribose 5-phosphate, this step is PRPP synthetase. Okay, ATP makes this, and we make PRPP. We're going to actually see PRPP is used actually for salvage pathways. Salvage pathways are once we make the purines, okay, or ingest them. Most of the time we make them. We've spent a lot of energy making that, putting all of those molecules together. We want to maintain it, and so what we're going to do is save the purines. We're going to break them off of the deoxyform or the oxyform, okay, and then we're going to effectively put them back onto PRPP, and so we're going to regenerate them, okay. This is not the rate-limiting step because there are other pathways. Remember, rate-limiting step means the step where once you commit to that step, going through that step, you're going to a certain product, okay, which would be whatever, okay? So, all right. This is the rate-limiting step, glutamine phosphoribosylate aminotransferase, the glutamine coming in, and we get this for the amino group. The amino group here has come from the glutamine amide, okay? And that's the rate-limiting step. You need to know the rate-limiting step because you want to be able to look at what's going on. So here's the structure of hypoxanthine up here, right? And it's on a sugar and a phosphate, so it's an IMP, it's a nucleotide. Okay, all right. This is the synthesis of AMP. So we're going to start with IMP, and we're going to get AMP, all right? So what's the difference between this and this? Structurally. The starting material and the air, what's the difference? The oxygen has been replaced by an amino group, okay? All right? Everybody comfortable with that? Okay. So what's going to happen? All right. Now, I'm making aspartate. Because of controlling mechanisms, the energy form that is actually going to allow the aspartate to do it. So the energy form will be GTP, okay? And the donor form will begin with A. So the donor nitrogen is going to come from aspartate. So A goes to A, energy G for doing that, okay? And it will make sense when we see the next one, which is GMP, all right? We get adenylyl succinate, okay? Fumarate, the aspartate has donated, and it comes out as fumaric acid. And then the nitrogen gets left in this position, and it comes out that way, and we get AMP. Okay, and if we want to make ADP, then we phosphorylate it again, and then we do another one for ATP, and we do it that way with kinases. Okay, good. Everybody see that? So the donor is A, the product is A, the energy is G. So I'm getting a level of control that I want to have a balance between the purines on that basis, and we'll see this in a minute. Okay. This is IMP, and we're going to GMP. Okay? So what happens in this situation is GMP has an amino group in this position and a carbonyl in this position. All right? So it's more oxidized, okay, than IMP. Okay? Everybody see that? Okay. So now what's going to happen is this is therefore going to be oxidized, and so IMP is going to be oxidized, and I'm going to put another carbonyl in that position, okay? So that one is xanthine. That was xanthine, which is less oxidized than xanthine. Everybody see that? Okay. And now what's going to happen is the energy for the donor is going to be glutamine, okay, going to glutamate. The energy is going to be from A. So G donor goes to G product. Energy is the opposite. It's A to A, just like in the other way. Okay, is that making sense to people? So it's, the synthesis of each of the compounds is really dependent on what else is going on in the other form. Okay, and we get GMP, which has an amino group there. Okay, and then okay, so this is kind of the control of the two pathways. Okay. GMP, GDP, GTP actually all go back to the rate-limiting enzyme. So this is end product inhibition for G, and this is end product inhibition for A. Okay, so we're controlling the synthesis of ATP and its derivatives, or an AMP, with GMP and dealing with it that way. Okay, so that's what the process is. Okay. Okay. I'm going to hold this because I'm going to just point about this, and the reason for it is that there are inborn errors in these enzymes, okay, and this is now what's happening. We have 3 minutes before I have to stop, okay, so we're going to pick this up because the next lecture is actually called nucleotides. And it's really pyrimidines, okay, and we're going to do, so it makes sense at the next lecture. We'll be dealing with it, okay? So one of the things, let's take a look at adenine, okay? Adenine is free, so I freed it, okay? We'll show you how you can free it, okay, from its nucleotide or its nucleoside, okay? And it's worked on by an enzyme, adenine phosphoribosyl transferase. Takes PRPP, the PP goes off, and we get AMP, okay, on that way. So we're actually salvaging it on that basis, okay? Then a nucleotidase is going to do what? So a nucleotidase is going to work on a nucleotide and take off its phosphate, one phosphate, okay? And therefore I get adenosine on that basis, okay? All right. All right. Now what happens is adenosine is the only base that has a deaminase, and it's going to take the amino group out, and I'm going to get it, right? So structurally, I'm going to get inosine, okay? And then you're going to follow it that way, okay? The one that is really interesting, a deficiency of this one does the same thing for hypoxanthine and guanine, and makes the IMP in this case and the GMP in this case, okay? This enzyme is called hypoxanthine guanine phosphoribosyl transferase, okay? Its deficiency disease is called Lesch-Nyhan disease. Does anybody know what the presentation of Lesch-Nyhan's disease is? What? What?
Do you mean like the symptoms?
Yeah.
Like do you have like self-mutilation?
Self-mutilation. They bite their fingertips off and they chew their cheeks, okay? And that's the deficiency of that disease, okay? So that one becomes an important one for you to know. I'm going to start right there. I'll answer some questions because you have at least 1 minute, okay? All right. I said right on time.